Welcome, everyone. Thanks so much for joining us today. This is Get Started with Essential Physics, Part 2, which focuses on hands-on investigations, particularly those with PASCO wireless sensors and SPARKvue software. This is one of two sessions we're doing today about getting started with the Essential Physics textbook program. Part 1, held earlier today and soon available for viewing as a recording, focused on the books, specifically the student textbook, the student ebook, and the teacher ebook and resources. Without much reference to hands-on investigations, aside from one that uses a simulation and some typical lab equipment. Part 2 that we're in right now is going to focus on this hands-on student investigations integrated into Essential Physics, and in particular, those that use equipment from PASCO's Essential Physics equipment kits, and especially those that use sensors and SPARKvue software to allow students to do investigations that involve data collection and, most importantly, analysis and interpretation of that data. You can watch past recordings by going to pasco.com/pd and sign up for future live webinars there as well. And Kane, I believe, will put that in the live chat if you wish to sign up for things in the future or view previous recordings that are archived there on our website at pasco.com/pd. So what's our agenda for today? Well, we're going to kind of alternate between some general information topics and diving into specific investigations to illuminate some of those topics. So after a quick overview of the Essential Physics program and the resources available, we will dive into the first investigation, our first investigation today, and the first investigation in the book, which covers graphs of motion with the smart cart. Then we'll pull back and talk a little bit about the equipment kits and SPARKvue software available for use with the Essential Physics investigations. We'll continue then with another deeper dive into an investigation that's fairly complex, but allows students to discover the relationship between force and acceleration for a smart cart through Newton's second law. We'll talk about some of the opportunities for sharing data from SPARKvue, getting student responses, and some of the additional supports available for investigations in circumstances that might not allow you or your students to do these investigations face-to-face in class. And finally, we'll end with an investigation from the electricity and magnetism unit on resistors and Ohm's law. All right. First up, though, for those of you kindly joining us live, let me pop open a poll and ask you to share with us your experience level with Essential Physics. So in a moment, your screen will come up with a poll, and this poll asks, which best describes your experience level with Essential Physics 3rd edition curriculum? Are you just taking a look for now? Have you adopted it but haven't used it yet? You might have just adopted it in your school or district and be looking at it for the coming school year, for example. Or have you already used it in class with students? So the responses are coming in. Thank you for your participation. And in just a moment, I'll close the poll when the responses stop and share the results so we can get a sense for what level of experience you and your colleagues have. All right, here we go. Thanks for your responses, and here they are. Seems like the majority of you, 75%, are just looking for now. Fantastic. I hope this gives you a good overview of the hands-on sensor components of Essential Physics. A quarter of you have adopted but haven't used it yet. Fantastic. So as we go through today, please don't hesitate to ask us questions in the Q&A panel, make comments to make sure we're addressing your needs. And thanks for participating in that panel. All right, so a little bit about the Essential Physics 3rd edition program. I want to preface this by saying we go into much more depth in part 1. So if you didn't attend part 1, feel free to pause and look at the recording in the future if you're watching the recording of this session. But a quick overview so that we know the context for where these investigations lie within the program. So the Essential Physics program consists of a student textbook. The student textbook is about a 900-page textbook. And one of the hallmarks of this is the integration of investigations in the textbook. The textbook has some interactivity in the form of a student ebook, which replicates the physical book, but adds interactive elements from interactive equations to videos to interactive simulation investigations. There's a corresponding teacher ebook that provides a bunch of resources, from handouts that you can give to students with or without modifications, customizations, to slides that you can present to them, and a lot of resources that will help you to deliver this content to your students and engage them in the topics of Essential Physics. Accompanying that is an infinite test bank covered in part 1. It allows you to generate things like end of chapter exams that are completely novel. Multiple copies of it. And finally, a PASCO Physics Academy. We're going to hit upon the PASCO Physics Academy again in part 2 to talk a little bit more because it is very centered around investigations. Also available in this program, if you adopted, are equipment kits, different levels of equipment kits. We will definitely focus on that today. And among those equipment kits are traditional things like lenses and light sources and springs, along with some of PASCO's wireless sensors, from things like sound sensor to a photo gate to voltage and current sensors, and the wireless smart cart, which looks like a traditional low friction cart, but has sensors integrated into it to measure things like position, velocity, acceleration, and force. It's going to be this equipment kits today, and in particular, those activities that involve sensors that we're going to focus on in this part 2 session. Those sensors do require that you have some sort of data collection and visualization from the sensor data. And for that, we'll be using the SPARKvue software. So more on the equipment kits and SPARKvue software in a bit, but that bottom row integrated with the resources from the top row will be the focus of this session number 2. As mentioned in part number 1, there are different ways to get the teacher resources. One of those is to have gotten the teacher edition access codes for Essential Physics and get them from the sidebar in the book. More on that in a bit, and a lot more on that in part 1. But you can also access the things in this blue bubble in the PASCO portal, which is a school-based subscription, a very affordable subscription for schools that gives you access to Essential Physics, Essential Chemistry, and many other things from PASCO. Today, we're going to both look at how to get information out of the ebook, teacher ebook, and from the PASCO Academy in alternating activities. But if you want more detail, please do see part 1. Student and teacher ebook access is available at the same website at education.pasco.com, and it's based on having student access codes. Once you log in to this site, if you're the teacher access code, you'll see things like Open Book, Test Bank, and Academy. Alternatively, you can access both of those from the PASCO portal at portal.pasco.com. And in PASCO portal, you have the same access to logging in with a portal account and going to the curriculum for Essential Science, where we have Essential Physics, and all the teacher resources are included with every portal subscription. The student resources are included if your school or district has adopted and purchased the keys to have student access. But even if you've never heard of Essential Physics before today, if your school has gotten you a subscription to Portal as part of a school subscription, you do have access to all the teacher resources for Essential Physics within PASCO Portal under the curriculum PASCO Essential Science selection. All right, see part 1 for a lot more details on that. PASCO portal, you can get some more information about the portal itself at our website, pasco.com/portal, which Kane has kindly shared there in the chat. And to log in, as I just did, you can go to the actual portal website at portal.pasco.com, which gives you options to log in depending on how your district or school has configured it, by email, a single sign-on tool like ClassLink or Clever, perhaps your Google account associated with school, or your district may even have put it on an SSO or single sign-on tool like Classic or Clever. So we'll see more of the portal today and a lot more in part 1. So quick question for the quarter of you who have adopted Essential Physics. Do you know how you will be accessing it? So for that, I'm going to open up one more poll question. And this question asks, if you have Essential Physics, don't worry about responding if you don't. Do you access its resources through education.pasco.com, the option on the left here in my slide, or do you access it via PASCO portal? Or maybe you don't know yet, since many of you are just starting the year, starting with the adoption of Essential Physics. All right. Leave it open for a few more seconds. All right, fantastic. So those of you who have adopted, I know none of you have actually dived into this yet with your students, but here you can see in the live session that about equal numbers of you are accessing via education.pasco.com and PASCO portal, and half of you aren't sure yet. So it's something to talk to your science supervisors, science department chair, or IT folks about access if you know you're adopting it this school year. But as I mentioned, more on this in part 1, and I'm going to demonstrate both of these sources, education.pasco.com and the PASCO portal, here in today's session. All right. So in either case, you're accessing teacher resources in the ebook itself, the teacher ebook. It's in the sidebar. We'll see an example of that in just a moment. And in PASCO portal, you can choose to view chapter resources, and everything you'd find in the teacher ebook sidebar is presented in a different format that has some advantages for distribution to students that we'll talk about in the middle of today's session. Among those lesson resources are lesson plans to help guide you, the instructor, on what students need to know going into an activity, what equipment might be needed if it's a physical hands-on activity, how you might introduce it, and what is some evidence that you can use to assess your students' learning. There's a set of instructor slides that you can use to introduce the topics and help guide students through the investigation. We'll be looking at both slides and student work in a moment. In the case of investigations, there's something called student work that consists of a handout that you can give students that guides them through the basics of the investigation and provides a place for them to respond to questions about the investigation. And for that investigation student work, there is a corresponding teacher key showing representative data and answers. And for all of the activities that use equipment from PASCO's kits with sensors, there is a teacher video that guides you through it. So we'll be taking a look at key components of this in the first example in a few minutes, but these are the types of lesson resources that are available either from the teacher ebook sidebar or from the PASCO portal, depending on how you're accessing your essential physics resources. All right, so as mentioned in part one, I just want to mention, make sure you're aware that there are about 90 investigations in essential physics, and many of them are just investigations that can be done with or without PASCO equipment. These are simulations like wave interactions, orbital simulations, and more advanced physics topics like Rutherford scattering simulations. And these investigations are in the student ebook and have accompanying materials for you, the teacher, to help guide students through them. They happen to not require any physical equipment. There are a lot of them, dozens and dozens of them in the book. And they're also available as a web page link that you could share if you don't want students accessing from the ebook if you have the PASCO portal access. However, in today's session, we are going to be focusing on those hands-on investigations that use sensors like smart carts. All right, so for the first investigation, we're going to take a look at the first investigation in the book. One of the hallmarks of the Essential Physics program is that the investigations were created when the book was written and aren't just tacked on. So once you and students get into the beginning of this upcoming school year and flip through the book, chapter 1 is about the science of physics, and it takes only one page flip to get to the first investigation. And one of the places you can find investigations in the book is embedded in the student textbook itself, including here on page 5, whether you're looking at the physical textbook or the online student ebook, you'll see that the first investigation, 1A, is called graphs of motion. Now, this isn't about learning kinematics. It's about learning the domains of physics. In this case, physics studies things like motion. Now, the page itself in the book has some of the information that students could use to do this investigation, but there's also resources in the teacher ebook that we'll look at momentarily, and one of those is a student handout. And that student handout has instructions to students for doing the lab and a place for them to respond. This handout comes in many forms. It comes in an editable form, like a Word doc. It also comes in a PDF that you can simply print out if you're happy with it as is, or use electronically as a PDF. And we're going to look at those different avenues throughout the activities that we're doing today. This activity, if I were to look at the book, requires only let's actually do that. So if I open the teacher book in this case and go to the investigations 1A, you'll see these documents that we were talking about, the lesson plan. If I were to look at the lesson plan, it would tell me what materials I need for this particular investigation. I could print out or modify the student work, which is what I have printed out here in the live video. And there are slides that I can use to guide my students through it and introduce the topics about physics and in graphs of motion. I have taken some of those slides because it's an editable PowerPoint and incorporated them into my slideshow today. So whenever you see a blue border like this is a slide I've taken directly from those as a representation of the supports that are available to you, along with things like the student handout. All right. So let us jump into this particular investigation. Again, not so much about kinematics, but getting students engaged with data collection, some of the equipment that they'll use once we get to the mechanics chapters, a few chapters in, starting with chapter 3. And the core of this is using the smart cart. The smart cart, as I said earlier, is a low friction cart that has sensors embedded in it. And these sensors allow us to measure the rotation of the wheels. And as long as they're not slipping on the track or just table surface that it's rolling on, this cart will report to our SPARKvue software the cart's position and derive from that its velocity and acceleration. It has also a force sensor built into it. And to this force sensor, we can connect things like hooks and bumpers to look at what sort of forces are applied to the cart when it is moving and see the corresponding position, velocity, acceleration changes. There's also a gyroscope built in for rotational measurements and an accelerometer for three-dimensional measurements. But today we're going to focus on the main measurements of position, velocity, acceleration from those rolling wheels. And in the Newton's second law investigation later, we'll hook something up to this force sensor. But starting with the slides here provided to you as the instructor in the teacher resources, you could use these to guide students through this. You could also give them the handout or do both, depending on what would work best. Knowing that this is the first investigation in the book, I'm going to model that I'm kind of walking my students through this because there's a lot of new stuff here. I will note that the slides have more information and more details than the handout does, so that the handout stays nice and concise if you are printing it. And because this is available in PowerPoint form, it is completely editable, so you can change the PowerPoint and customize it for you and your students' needs. And I've made a few customizations to these slides that I'll point out in a minute. But fundamentally, this is asking students to open an experiment file, power on the smart cart, which is an example of a wireless sensor, and then connect it to SPARKvue. So this is first time they will have done this. This, for many of you, will be the first time you'll have done this. So I'm going to walk through this step by step. The first thing we need to know is that we're going to use software called SPARKvue. I'll provide you some more details on what platform SPARKvue is available on in a little bit. But for now, let me launch SPARKvue on my Windows computer. And on my particular Windows computer, I have installed the SPARKvue software. Again, more on that in a bit. And when you launch SPARKvue, no matter on what platform, it opens to what we call the welcome screen that gives you some options for how you want to enter SPARKvue for commonly used routes. Now, for all of the essential physics, you're going to see an instruction to students like this. Open the experiment file, name of experiment file. So in all those cases, we have built the essential physics experiment files for SPARKvue into the application itself. So you don't need to distribute the SPARKvue files because it is built in. How do you get to it? We start with open PASCO experiment, this entry point here in the lower left. And when we do, we'll see there's some configuration files built into SPARKvue for essential chemistry, our lab stations, and of course, for essential physics. So I'll open the essential physics folder, and here we can see a list of all the starting files that are provided for essential physics inside SPARKvue. We're starting here with 01A, graphs of motion. So I'll open that up, and basically these starting files are configured with appropriate displays, settings like how often data is going to be recorded, any other conditions that make it easier for students to get to the data collection and analysis more quickly and not have to worry about setting things up for a particular experiment. In this case, we have a graph of position versus time on top and a graph of velocity versus time on the bottom. And the next step in our slides or in the student handout is that we need to power on the smart cart and connect it wirelessly to SPARKvue. So all of our wireless sensors have built-in batteries. That's also true of the smart cart, which in effect is a wireless sensor. And there's a power button on each of these wireless sensors, and you can press and hold the power button for a second. For a moment, you're going to see a LED light up next to the battery icon. That tells you just turn the sensor on. And although it may or may not come through, the Bluetooth light is blinking red. Depends on the refresh rate of our video feed. But when a Bluetooth light is blinking red, I know that my wireless sensor, like the smart card, is on and it's available to connect to SPARKvue. Our wireless sensors, as the Bluetooth light implies, use Bluetooth low energy connectivity. And the beauty of Bluetooth low energy is it doesn't matter what platform you're on, you can connect within the software. So I'm going to demonstrate that following this diagram shown here. And when I return to my file in SPARKvue, you can see there's a Bluetooth icon in the upper right. When I click on it, it opens what's called the wireless devices screen. And because my smart card is on, I can see it show up here in the list. Now, the smart card, I just have one right now, but I'll ask Kane to turn on another to better represent what you might see in the classroom. Kane's happens to be red, and I can see that in the icon, but you may have a set of blue, set of red. They're the same except for the color. What we can do, though, is determine which one is mine one of two ways. The first is that our programmers were clever and they put the strongest radio signal at the top of the list. So it's usually the case that the top of the list is the one closest to your computing device. But you can always confirm that by looking at the 6-digit ID that's printed on every one of our wireless sensors. In this case, 203-207. I can see next to the Bluetooth blinking light. And I can see that same number presented here in SPARKvue's wireless devices screen. So I'm going to click on my smart cart as identified by that 6-digit ID. And within SPARKvue, it's going to make that Bluetooth connection, a Bluetooth low energy connection to the cart. It will move up into the list of connected devices. Once a device sensor is connected, it's no longer available to anyone else in the classroom. But if there's an experiment, like a momentum conservation experiment that needs multiple carts, you can connect multiple sensors, but a sensor can only be connected to one version of SPARKvue at a time. That's all I need for this particular investigation. And now that I've connected my sensor, this start button becomes available as an indication that I'm ready to collect data because my cart is connected. So moving on, the next step in this investigation, whether you're using the slides as I am or the student handout, is to start data collection and simply move the smart cart back and forth on the tabletop. So I'll press the green start button at the bottom of SPARKvue, and I can move the cart back and forth rapidly, slowly, and just see that as I move the cart back and forth, we're getting a live plot of position versus time in the top plot area and the corresponding velocity versus time in the bottom plot area. I mentioned that the essential physics SPARKvue files are pre-configured. In this case, this is the first investigation. So you may have noticed I pressed start, but I never pressed stop. That's because this particular file is configured to stop data collection after 10 seconds. If I wanted to stop earlier, I could have pressed what was a red stop button there at the bottom. I'll do that in a little bit. But we now have a graph of position versus time and a corresponding graph of the cart's velocity versus time. Now, here's where I wanted to show you something extra that wasn't in the original slide. So I just edited the PowerPoint here, and I want to introduce you to some of the SPARKvue tools that you and your students are going to use throughout the year. Not so crucial for this particular investigation, but we have limited time together here, not the whole 2 semesters. So let me add to this important tool called Scale to Fit. And when we're using the graph and other displays in SPARKvue, we have a toolbar, in this case, the graph toolbar, that we can open like a tray and collapse if we don't need to see it. So I'll press the sole button down here in the lower left of the graph. It opens up a tray of tools. We'll look at quite a few of the core tools today, but the leftmost one, if I hover over it, pops open a tooltip that says this is Scale to Fit. What happens when I press Scale to Fit is that the X and Y axes of all the graph's plot areas adjust automatically so that the data itself is filling the screen as much as possible. All right, I can also move that legend around if it happens to be obscuring some of the data. So there's a better view of the data that I collected, and you can press Scale to Fit after or even during data collection to essentially zoom into the data. All right. So what do students do in this investigation? Well, they're asked to answer a couple of questions here. After they've learned that the cart and SPARKvue can report the cart's position and velocity, they are asked to simply push the smart cart across the floor and let go and see what happens to its velocity. So I'll do that by pushing the smart cart here to the side of your camera view. I'll once again press start and then give the cart a push. All right. And I could stop ahead of 10 seconds by hitting stop here. I'll let it go to 10 seconds though. And now it's handy to press Scale to Fit. And the question to students is what happened to the velocity versus time after you push that cart in Y? And we can see that I pushed the cart, it had a pretty high velocity, and then it slowly went down and down and down until it ultimately stopped at the far edge of your camera view here. All right. So what caused this? Students may introduce the idea of friction there or not. But again, it's not about the kinematics. It's kind of about data collection and interpretation here. I'm going to skip part B because it involves lifting the table, but let's go to part C. Try to move the smart cart across the table with a constant velocity. What's the shape of the position versus time graph if I achieve a constant velocity? So this time I'm going to hold on to the cart the whole time. You may have noticed that when I press start, it looks like previous runs of data. A run is what you get between pressing start and stop, have disappeared. It turns out they've just been hidden to keep the graph screen clean, but I can always go back to this graph legend and click this button to turn on the visibility of previous runs. So when I press start again and try to move this cart with constant velocity, I'll expect run 2 to disappear, but still be there if I want to turn it on via the legend. So let me hit start and try to move this at a constant velocity. I'll press stop to end it before the 10 seconds. Scale to Fit once again. And what did the velocity, the position versus time graph look like? Well, looks like a fairly straight line with a particular slope if I achieve a constant velocity by pushing. All right. So a quick introduction to some of the tools in SPARKvue. Now there's one final question I do want to investigate, and that is essential physics tries to make some connections between things like physics and other sciences, mathematics, engineering. In this case, it gets students starting to think about, well, how does a smart cart actually work? And it suggests trying to roll each wheel by hand and figure out if all the wheels track the motion. So I'm going to return to SPARKvue here and record a final run of data. I'll flip the card over so that you can see it. I'll press start and let me roll this wheel. I see that these two rear wheels are rolling together. Well, that doesn't seem to do anything. I'll roll the front wheels. There we go. So it looks like these front wheels rolling together might be the source of the readings of the smart card. And indeed, if we were to look this up on the PASCO website, we'd learn that there's an optical encoder in there that's doing a pretty high resolution job of determining if those front wheels are rotating. What do I mean by front? The front is where the force sensor connector is, and it's also where this big plus X is pointing. So this is the positive X direction from the cart's perspective. All right. So one final question, what is the smallest distance the smart cart can record? And this teacher slide suggests that students could drag the numbers to zoom in. So one of the ways we can change our view in the graph is to press scale to fit, as I showed before. But another way is that we can drag the numbers on these axes and stretch and compress the graph in either the X direction or the Y direction, as if it's made of rubber. So in this case, I'm going to stretch it out, and I can also click in the middle to pan around. And what I'm interested in is figuring out, well, how small a change in position can this possibly measure? And it looks like these might be some of the smaller position changes. And I can see it can go from about, well, 0.000 meters to 0.001 meters. And I could do that by looking at the graph axes, or there are some tools that can help as well. One of those tools is called coordinates. But before I use coordinates, well, let me show you. I can press coordinates and it plops down here on velocity versus time. So one more advanced topic that I've added to this slide is an introduction to this idea that if you're looking at multiple measurements like position and velocity, you need to tell SPARKvue's graph which one is active, which one's of interest at any one time before you select a tool for analysis. So I'm going to make sure that my Y1 measurement, my position measurement, is active by clicking on its symbol in the legend. I get a red box around it. And now when I turn on coordinates tool, I can drop it on any of these position measurements, and I can move around and see that indeed it looks like maybe I'm getting a 0.1 millimeter resolution between the smallest difference in measurements of position. So pretty high resolution and an introduction to how the smart card actually makes its measurements. So as long as those wheels are rolling without slipping, you're going to get a good representation of the cart's position, velocity, and acceleration. All right. This lab continues. I'm not going to do all of part 2 or part 3, but it's important to know that SPARKvue files in Essential Physics can have multiple pages. In this case, it asks students to go to page 2 in the SPARKvue file. And in this case, we could hide our prior runs, knowing that they would also disappear. And it's asking students to do kind of a more traditional match graph challenge. Can you make a shape like this? Can you make a shape like that? What's the difference between the two motions to get that? So the first shape is something like this. And it will end at 10 seconds. And more like the traditional match graph activity that you may be familiar with. All right. So again, not about kinematics, but a little bit introduction to making measurements in a nice little challenge there. So we've seen how we can use sensors like the smart cart and SPARKvue software to collect and do some basic data analysis, with some key points that all Essential Physics labs begin by opening a provided file that's built into SPARKvue. And students can either proceed with written instructions that you can get from the the teacher ebook sidebar, PASCO portal, or you can use the slides with or without customization, as I've been doing here, to guide students through the activity. Kate, any questions about that approach before we continue? Okay, thank you for. All right, fantastic. Thanks for addressing those questions already in the chat and Q&A. All right, so continuing on here, let's talk a little bit more about those resources. Again, the student textbook and ebook have the basics of an investigation embedded in the appropriate place within the book, but it's the teacher ebook and the portal. But in this case, let's look at the teacher ebook where you can get additional resources. So those resources for every investigation include the lesson plan that talks about the equipment and the context for the investigation and ways to assess it. It has a teacher video. This is a teacher to teacher video. One of my colleagues described it well as if you we're scrambling to get ready for a lab tomorrow and figure out, how do I do this, or is it worth doing? This is a conversation with a colleague, an experienced veteran physics teacher in the hall for a few minutes. These are typically 3 to 10 minutes. I'm going to play the start of this one and just scrub through it so you can get a sense of what sort of content is provided. So back in the teacher ebook for Investigation 1A, we'll see that there is a teacher video. And again, this is teacher to teacher, physics teacher to physics teacher. And this video is going to present first an introduction to the concept of
What do graphs of motion look like? This is the question that students will explore in Investigation 1A, graphs of motion.
It goes on to introduce
motion. In
the lab
particular,
itself.
they do not
And in this case, it talks about
data that represents
doing each
the
of the
motion of the
parts
cart.
and doing a demonstration
Students
to
begin by
you for the
opening
basics.
the SPARKvue experiment file indicated in their student handout. This file is titled 1A, Graphs of Motion.
And since this happens to be the first investigation, this goes into a little more detail about the basics of getting to that file. But you'll see an example of the data collection. This doesn't do the entire thing, but it does as concise a job as we think can be done to convey to you what the core of each of these parts is, and introduces key data collection and analysis tools in case you're new to SPARKvue. So that's the teacher video. Besides preparing to do the investigation, I think these teacher videos are great at giving you an orientation to whether you should do it. It's a great 3 to 5, 10-minute way to see, what is this lab all about, and is it worth doing with my students? All right. So continuing down the resources, we have the slides. Again, customizable PowerPoint or ready-to-view PDF for guiding students through the investigation. We tend to have more slides than you can probably deliver in the time you have or want to deliver. That's with the philosophy that it's easier to trim slides down than to create your own slides. Next up is the student handout that we saw already, and then there's an answer key for that student handout with correct answers in the case of correct answers, or representative data in the case of investigations. All right, so that was a preview of an investigation that uses the smart cart. We're going to see the smart cart again in the next investigation, but I want to pause here and talk a little bit more about the SPARKvue software and the equipment kits available for Essential Physics. Currently, we have 2 kits available for Essential Physics. The first is called the Standard Kit, and it consists of a mechanics bundle paired with an E&M bundle, electricity and magnetism. And with the Standard Kit, there is PASCO equipment for doing 23 of the 90 or so investigations in the Essential Physics textbook. Recalling again that many of those investigations are simulations that don't require equipment. You can do 23 core investigations with the Standard Kit, plus additional materials, typical lab things like thread. There's also available the comprehensive kit, which basically starts with the same 2 kits, the electricity and magnetism kit and the mechanics kit, and adds to it a mechanics extension that includes a second smart cart for things like collisions, a photo gate, and a projectile launcher, and some accessories for things like pendulum experiments. So this is the mechanics extension kit. And that is paired with 2 other kits in the comprehensive kit that are in addition to the standard kit. We have a sound and waves kit and an optics kit. So these are basically 5 kits together that comprise the comprehensive kit. And you can do 37 of the investigations with materials from this kit, or 23 with the standard kit. Now, we have had Essential Physics 3rd edition for quite a few years now, and when it was first released in 2018, 2019, we had a slightly different set of materials. It was also called Standard and Comprehensive Kits, but there were some different materials that have since been replaced by different materials. What I want to emphasize here is that whether you're using the previous equipment kits or the current equipment kits, Essential Physics supports both of those. If you want a quick way to tell which kits you're using, one thing I look to is, what does the rod stand look like in your kit? In the case of the current kits, it's a circular rod with a heavy A base. In the case of the previous kits, it's a rectangular cross-section rod with a tripod that you assemble out of 2 different pieces. All right. Crucially, though, we support both of those kits in the investigations in Essential Physics. And how do we support it? Well, a lot of times there's no difference, but where there is a meaningful difference, what we've done is provided files in the teacher materials for both of those kits. So you'll see these kits labeled as Equipment A for the original kit and Equipment B for the current kit. And in the book, you'll see something, for example, that shows if you're using equipment kit A, here are the student work and answer files. And if you're using equipment kit B, here are the corresponding files. All right, so let us know in Q&A if you have any questions about equipment. Moving on to the software, though, I demonstrated SPARKvue as an installed application on my Windows computer, but the key thing I want to convey here is that SPARKvue is available on pretty much any platform that's used in education today. So those include Windows, Mac OS computers, Chromebooks, iPhones, iPads, Android phones and tablets, and dedicated Spark data loggers from PASCO. Now, how you get that software on the platform varies depending on platform. So I have a little table here that will talk about those. Now, if you want to install the full SPARKvue application, as I have on my Windows computer, on Windows and Mac, it's a licensed application. Your district or school may have purchased a license for SPARKvue, typically a site license that gives you the ability to install it on all your school computers. And in that case, you would get the licensed installer from your IT folks and install it on Windows and Mac. Chrome OS, there used to be a license, or rather, there used to be a free application from the Chrome Web Store, but Google is sunsetting the Chrome Web Store for applications like that. Your district may still have it installed. If so, great. If not, I'll show you that there's an alternative for the very popular Chromebooks. And SPARKvue is a free app for installation on iOS and on Android. And of course, it's installed already on PASCO's devices. All right, so you're probably curious about, so what do you do on Chrome these days? Well, what we did when Google indicated that the Chrome Web Store was going away is we created a version of SPARKvue that is what's called a progressive web app. And this is basically an app that is SPARKvue that runs inside appropriate or inside supported browsers. And it's available on 3 platforms. So it's available on Windows, on the Chrome and Edge browsers, available on Mac OS on Chrome and Edge browsers, and available on Chrome OS in the Chrome browser. And what's key here is that it is a free tool. So you simply go to the website. Kane has kindly pasted that, sparkvue.pasco.com. I'll demo it shortly. And it will run SPARKvue inside the browser. So looking across all these platforms, you'll see that there is a free option to use SPARKvue on all these platforms. And SPARKvue, the installed application, runs pretty much the same as SPARKvue, the progressive web app, with one exception, and that is how you connect sensors. And I'll be demoing that in the progressive web app shortly. One thing to know is that if you do prefer the SPARKvue application and you subscribe to Portal, Portal includes licensed installers for SPARKvue, the application for Windows and Mac. And you can find that inside Portal by going to the support section, and you'll see that under software downloads. All right. For more information on SPARKvue in general, you can go to pasco.com/SPARKvue. And once again, let us know live here in Q&A if you have any questions about SPARKvue access. Bottom line, it's going to run on all the platforms that you probably have in your classroom, runs pretty much the same. And the big distinction is whether it's installed or running in a web browser. All right, so for this next investigation, we are going to use SPARKvue as the progressive web app, and you'll see how similar it is to our first experience here. This time around, we're going to do a more involved lab that comes in Chapter 5. I didn't mention earlier, but by the way, when you see investigations like 5A, the number indicates the chapter, and then A is simply the order of the labs within the chapter. So I know that 5A is the first investigation in Chapter A. Excuse me, first investigation in Chapter 5. All right. So let's look at the resources for this investigation in Portal. Again, these same resources are available in the teacher sidebar, but this time around, let's bias it towards the portal since half of you are accessing via the portal. And I'm going to jump over to the PASCO portal here. Again, you can log into Portal depending on how your IT is set it up with email, with single sign-on options like Clever, Google, or ClassLink. Mine is via email, so I'm going to log in. I'm going to go to the menu, choose Curriculum, and PASCO Essential Science. And I could launch the ebook right here, but I'm going to dive directly into the resources that are extracted from that ebook and placed into a convenient view inside Portal by going to View Chapter Resources. Chapter 5 holds Investigation 5A, and it is in Lesson 4 called Newton's Second Law. So all those resources that would be in the sidebar in the Essential Physics Teacher Edition ebook are available here and laid out nicely in the portal. We'll talk a little bit more about what you can do with portal files, but now let's just acknowledge that all the files in that sidebar are collected here. So in this example, we have slides, of course, that we can use to guide students through it. In this case, I'm going to focus on the actual student instructions to guide me through this. Students are probably working a little more independently by this time. So in this time, I'm actually going to download the Word version, not the PDF, but the Word version. And here's where we see that distinction between equipment A and equipment B. And in this example, I happen to have equipment set B. The only real difference here is that the masses in this equipment set B are little marked masses of 20 grams as opposed to washers in equipment set A. But that distinction is known and conveyed in this equipment B. So let me download the Word document and open that up. Of course, we could edit the Word document and provide a change version of it to our students, or we could just use it directly. Here it is. And I'm going to use it directly. You may or may not want to provide students with the Word document, but one of the benefits of it is, of course, it's editable by them as well as by you, and I might use it instead of printing it out by typing directly into this Word document as we collect data for Newton's second law. All right, so in Newton's second law, we are going to see if we can discover the relationship between an object acceleration and the net force applied to it. The object is going to be that red smart cart that we see on the track in the live video view. And the forces we're going to apply to it are going to be provided by different hanging masses that are hanging off of a pulley. The smart cart, as shown in this diagram, is connected to the pulley mass via a light thread that I've leveled out. I have a couple of masses inside the cart to make it a little more massive so that we don't get crazy accelerations. And this lab is going to guide students through doing 5 different trials, and each trial a different mass will be added to the hanger to apply a different force to the cart and see the resulting acceleration. Of course, there are slides to support this. I've pulled out a couple of key slides here. One is from the teacher version of the slides. One is the physical setup that we could project to students to ensure they've set it up. I will note one more thing I forgot to mention. We are using both force measurements and velocity measurements from the cart. We've already learned that the velocity measurements come from the cart's wheels. In this case, on the red smart cart you see in this view of my video, we've attached a hook to that force sensor so that it can measure the forces applied to that cart by the thread tension directly. Now, when we do use, last step here, we need to open the file as we did earlier. And as I promised, this time around, instead of using the installed SPARKvue application like we did previously, I'm going to close that and open either the Edge or Chrome browser on my computer and go to the SPARKvue PWA URL, which is sparkvue.pasco.com. And again, this is a free app, and aside from it being in the browser, this pretty much looks like the SPARKvue homepage that you've seen when I launched the earlier version. What happened there behind the scenes is I haven't used it in this browser recently, so you may have noticed that it automatically updates. So one of the benefits of using PWA is the auto updates to make sure that you're up to date. But as we did earlier, we're going to do the same thing, try to find the experiment file, in this case 5A, by going to Open PASCO Experiments, Essential Physics, 5A Newton's second law, and we'll open that up. And it has a configuration file that on its first page includes plots of velocity versus time and force versus time. And ultimately, we're going to get from this the acceleration of the cart when different forces are applied. We're going to do a much deeper analysis this time around, though. Now, we need to hook up the cart, connect it. This time around, though, we are in the SPARKvue PWA, and this is the key difference between the PWA and the installed SPARKvue application. And that difference is in the PWA, it's the browser that needs to connect to the sensor. So I'm turning on my smart cart, my red smart cart there. And we're going to start the same way we did to connect a sensor in the installed app in the PWA, and we'll go to the Bluetooth button. But here the distinction is SPARKvue can't take over because it's in a browser to connect your sensor. So it's going to refer you to the browser's Bluetooth dialog by clicking this Bluetooth icon. And in this case, it's going to open up my Edge Bluetooth pairing window. This will look slightly different depending on Edge or Chrome, but in each case, we can still use the 6-digit ID on our carts. In this case, I'm going to hook up to this cart right here. We lose the priority order that the app knows about because the browser doesn't know about that, but I'm going to identify it by the 6-digit ID. My red smart card is number 456655, and I'm going to pair it in the browser. And right now, my Edge browser is making the connection via Bluetooth Low Energy to the red smart cart. It may take a little while, but once it succeeds, it is basically going to give SPARKvue permission to use that device. And from now on, you can see that this smart card has connected as if I'm in either version of SPARKvue. So I can press done, and I'm ready to collect data here in the SPARKvue PWA. And from now on, everything behaves just the same as it did in the native app. All right. Ken, any questions about PWA so far before we proceed with data collection? Well, all right, thanks. None so far about PWA, but feel free to keep those questions coming, and Kane's answering them. Excuse me. All right, so before we actually collect data, there's one key thing to know here. The live data bar in SPARKvue shows us what force is being applied to the cart right now, even before we hit start. I'm going to make sure no force is applied to the cart by removing the mass here, so the string is loose. And at this point, I would expect in a perfect world that this force should read 0 newtons. But the cart is measuring a little bit of force here, 0.14 newtons. So as instructed to students and here in the slide, what I'm going to do is make sure that it reads 0 with no force applied by going to this live data bar, which is a readout and a button, clicking on it and choosing 0 sensor now. And now its readout is going to be 0 or close to 0. I can reconnect the mass to the thread, hang it over the pulley, and I should be ready to collect the first data point, which by the way is with 20 gram mass on the hanger. All right. So as I mentioned, in this investigation, students will be recording 5 runs, and each of those runs is a trial with a different mass on the hanger. This first mass is going to be 20 grams. It's a little hard to view there. It's out of view, but I'm going to make sure that mass hanger is not swinging before I go to the start button. I don't have a long arm, so I'm using a ruler here to release the cart. So hit start. We can see the live data streaming there in velocity and force. I'll let the cart start rolling and grab it before it hits, and then I can press the stop button. We'll use that scale to fit tool we learned earlier, and now I can see nice graphs of velocity versus time on the top and force versus time on the bottom. Now, if we look at the student handout here, we are being asked to record 5 different trials, adding 20 grams at a time. All right. So I'm going to do one more trial here, and then because it's just rinse and repeat, I will then show you how students can do the analysis once they've collected all 5 runs. So I'm going to add 20 more grams for a total of 40 grams plus the hanger mass. Let it settle. Press start again. And release the cart. Grab it. Hit stop. And scale to fit. And now I'll turn on both the visibility run 1 and run 2 and scale to fit again. And we can see that run 1 here in pink for velocity versus time has a lower slope than run 2, and we can expect that trend to continue. We can also see the differences in force for the corresponding time. Once I released the cart, we can see that the tension lowered, and we could measure the applied force here directly. So in this investigation, students will be looking at the acceleration as the slope of velocity versus time in the appropriate area after the cart was released and before it was grabbed, and the corresponding force versus time. So the next question is, how do we do that analysis? How can students do that analysis? And of course, the slides provide some insights into that. Here, students need to be aware of this concept of active run, and then we're going to use 2 different tools to do this analysis. So let me go back and do the analysis for the first run of our data set. So to figure out the acceleration, we need to note that we're actually looking at velocity versus time. So one way to find acceleration from that is to find the slope of the velocity versus time curve. And what we can do is go down to our graph toolbar. We need to make sure that our velocity measurement is the active run here in the legend. It is, as indicated by that red square. So I'm going to turn on what's called the linear fit tool, and it's going to apply a linear fit and do its best to make a linear fit to, well, to the entire run. So by default, analysis tools like the fits or statistical analyses apply to an entire run. But what we really want to do is just analyze the slope of this portion of the run after I'd released the cart and before I grabbed it. So for that, we have something called a move toggle select tool. This tool right here has a hand, which by default allows you to move the graph. And because this file is configured, it was actually configured to be in select mode. What I can do in select mode is simply click and drag a box. And notice that as I drag that box, the data inside the box gets highlighted in yellow, and that linear fit adapts live so that I'm analyzing only the data inside the box. I can subsequently move the box. I can resize it by grabbing the corner handles. In this case, I want to analyze what is the acceleration that is the slope of this linear fit during the time after I'd released the cart and before I grabbed it. And from this, we can see it was about 0.261, and that would be meters per second squared. All right, now we need to analyze the corresponding force applied to the cart. And again, because the cart has a built-in force sensor, we're measuring that directly as the force applied to the cart as its force sensor. So for this, I'm going to make sure the lower plot is active. So Y2's measurement is active as shown in the legend. And now I'm going to turn on what's called the statistics tool. The statistics tool will do a variety of analyses. In this case, I'd like to find the mean force. But when I press OK, it finds the mean force, but we need to recognize it's finding it for the entire run once again. So 0.15 is quite a bit lower than I expect for the force in this area. So once again, we're going to use that selection tool, click and drag a box over the data points for when the cart was being accelerated after I'd released it and before I'd grabbed it. And from this, we can see that the mean or average force during that time period is 0.231 newtons. So depending on how your students are using this data, they could be going to a printout of the form, or they could be typing into an electronic version. So the force was 0.231 newtons, and the corresponding acceleration for run number one was 0.261 meters per second squared. Sorry, 0.261. All right. So you can imagine proceeding here and making run number two visible and active, doing the same analysis and continuing down the line there. I won't belabor that too much. What I have done is I have collected this data ahead of time and filled out the Word document with that data. So here is that same table filled out with another set of data collected earlier today. And I'm going to open up that SPARKvue file so we can just jump to the next step of this, which is analysis of that data. As I do that, Kane, let us know if there are any questions we should address to the whole group. Yeah. Yeah. Do you want to jump in and describe it on mic while I open this up, if you're okay with that?
Yeah, so Ken had a good question that I just wanted to bring up the cart. He said he stopped the cart with his hand. Will it be damaged if it hits the end of the track? And my answer is that not if it hits the end of the track, but with sufficient force and with 500 grams on it, the likelihood that it will just blow past the pulley and continue to the floor, which with the hook on it could damage the force sensor if it hits the ground with sufficient force. I have worked with a cart that had that problem. It actually still did work. It just had a 20 Newton shift that I had to zero out and account for whenever taking measurements. But obviously, the less you hit that force sensor, the better off for that sensor.
Yep, perfect. Thanks, Kane. Yeah, the sensitive part, as Kane mentioned, is the potential to bend that force beam inside the cart, and that has the potential to happen when you're doing collisions with accessories hooked to it. That leads to a general piece of advice, which is although the cart is robust, and I wouldn't feel bad about dropping it without an accessory on there, when you're not using a force accessory, it's best to take it off and store it without that so that you're reducing that risk. Great. Thanks for the question, and thanks for the response, Kane. So in this case, I collected this data earlier. Here are all 5 of the runs. You can see the progression of increasing masses and increasing accelerations. And this is where I got that data that I showed you. Now, the lab itself has students continuing to do some meta-analysis of this. They're going to take each of the accelerations that they've determined and the corresponding net forces that result in those accelerations, and go on to page 2 of this file. And on page 2, they're going to take that data that they have on their handout and they're going to put it in a table so that they can graph it and find any subsequent relationships. So let me quickly type in what you see in the Word document into SPARKvue. All right. And as I make these pairs, you're going to see that the graph on the right is going to graph point by point the data that I am entering in the table here of net force on the y-axis and acceleration on the x-axis. And there's the first point right there. And as I continue adding these pairs, we will see them populating in this table. There we go. All right. So it seems like we've discovered for this cart, there appears to be a linear relationship between the net force applied to the cart and the resulting acceleration. By the way, this file connects and graphs by default in SPARKvue connect the data points point by point, so it's easier to track. If you don't like that, one of the things your students can do is to go into the settings of the graph, and you can say, hey, turn off those connected lines. That's particularly useful when your challenge is to create a curve fit so that students aren't confused between the curve fit and the connecting lines by default, especially for linear fits like this. So students are finally asked to proceed and try to find out, is there a relationship between the variables? Well, it appears there's a linear one. So I'm going to turn on the linear fit. We used it earlier. And you can see here that the linear fit has a slope of about 0.773. And this handout guides students to begin thinking about, well, what are the units of that? Let's see, it's kilogram meters per second squared. So that's going to be kilograms since it's meters per second squared on the x-axis. So units are kilograms. And hey, it just so happens that we have a cart that's roughly 250 grams, and we have two 250-gram masses on it, essentially tripling the mass of the cart here. And it appears that the slope is somewhat close to 0.75 kilograms. So we seem to be deriving this idea that the constant proportionality between net force and acceleration might indeed be the object's mass. All right. And of course, there are some analysis questions here in the student handout to guide them through that. But that, in a nutshell, is this investigation. It's a more in-depth investigation where students are discovering this relationship between the object's acceleration and the applied net force. All right. So we've seen how we can get resources for investigations from the teacher ebook, and from there we can download files like the slideshow and the student handout. Those same files are available in PASCO portal. What does portal provide? Well, portal does provide a number of additional ways to distribute those files. You can still download files directly to your computer for perusing yourself or distributing to students as you would through normal means. You can also view those directly in a browser. So if there's a play button, you can view things like PDFs in the browser. And for example, remind yourself of the difference between the A and B versions of this. You can copy links for online files. I don't think there are, if I wanted to share this online version of this investigation, I could copy the link directly from, copy the link directly from PASCO portal for sharing with my students. I could also share to Google Classroom. So if you're a Google Classroom user, you could choose an individual file and choose to share it directly to Google Classroom, or you could even select multiple files and choose to share it to Google Classroom. And once you sign in, you have the ability to push it to a particular Google Classroom that you use. Some of you may have LMSs that aren't Google Classroom, and you may wonder, well, why isn't there a push to Canvas or push to Blackboard? And the reason for that is in the world of other LMSs besides Google Classroom, the model is that we have an app that your LMS administrators can plug in to your LMS, and it basically provides pull access. So within your LMS, like Canvas or Blackboard or Schoology, you can have that app installed. That is the PASCO portal app, and you can pull in the same files that you see here directly from the LMS side of things for distribution to your students. So Google Classroom is a push from model from portal to your LMS or to Classroom, whereas all the other LMSs are a pull model where you pull it from portal into your LMS once it's linked by your LMS administrators. And one final reminder, all these investigations that use SPARKvue begin by saying, open the investigation file, blah, 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 blah. You're never going to find that in either the portal or the sidebar of this teacher ebook. And that's because it is included inside SPARKvue itself under the PASCO experiment folder in Essential Physics. All right, so let us see, we're about 2/3 of the way through here. I want to talk a little bit about the options for your students to save and share data from SPARKvue. I saw that was a question asked earlier. So I'm going to talk about 3 different options. I want to preface this by saying, in most cases, this isn't a requirement for your students to do the experiment as written. I'll go back to this Word doc here of the student instructions, and you'll notice it has students sketching a copy of the graph in this case on a handout, for example. However, you may or may not want students to sketch. If you're doing an all electronic workflow, you may want them to save some time by simply taking an image of the graph. So I'm going to talk about some of the things students can do with data from SPARKvue once they've collected it, if you'd prefer to have an all electronic workflow. So I'm going to go back to my file, and the first thing I'd like to show you is that we can preserve everything about a SPARKvue file by saving it as a native SparkLab file that would have the extension .spklab. And that allows anyone to SPARKvue on any platform, even cross-platform, to reopen it later and do more analysis, or share it with a lab partner, or hand it in if you want to see the original data for your students. So I'm going to return to our file here, and if I wanted to preserve this, I can go to the main menu of SPARKvue, which is, sorry, the 3 bars in the upper left, and I could choose the option to save or save as. I'm going to choose to save as. I'll put it on my desktop, and in this case, I'm going to name this Newton's second data from lab group 3. All right, I can save that, and it preserves everything about this file. It can only be opened in SPARKvue, but as I mentioned, it could be opened across platforms and preserves everything about it, allowing you to continue collecting data if you reconnect sensors in the future, or to continue doing analysis. So it's always safe to preserve the entire SPARKvue file by saving it as a SparkLab file with the extension .spklab. A less used option, but of interest to some of you, would be that you could use SPARKvue just as a sensor data collection tool and use other tools like Excel or Google Sheets to do analysis. Now, SPARKvue has most of the analysis capabilities you would need, especially all those in Essential Physics. But if you wanted to use SPARKvue to collect data from sensors and then do cross-group analysis in a collaborative spreadsheet, you could export the data from SPARKvue. It's going to export it not in a format that is SPARKvue-centric, but in a very generic format by going to the main menu, Export Data, and it will save it in one of 2 options. The default is CSV for comma-separated values. The PWA only saves in CSV. The full app lets you to tab limited text as well. But let me save that to my desktop. I'll just leave it as exported data. And if I go to my desktop now, on my computer, CSV files are set up to open in Excel. They also open fine in pretty much any data analysis application like Google Sheets. And basically, this is all the data from the sensors and only the data from the sensors. So none of the displays that were in SPARKvue, like graphs and tables, none of the analyses that I did, but it is just the raw data from the sensors for all the runs that I collected. All right. So of limited interest, but for those who are interested in just getting the data, it is there for you. And finally, one more option, one that I think is most relevant for Essential Physics, and that is if the end objective of the lab is to find some relationship like we have between acceleration and net applied force, you could just use your operating system to take a screenshot of relevant displays in SPARKvue. So here are some shortcuts. iOS and Android have built-in sharing buttons in SPARKvue, but in things like Windows, Mac, and Chrome, we're going to use the operating system shortcuts. I'm on a Windows machine, so I'm going to press Windows Shift S. And what I'd like to do is capture this graph. So I'm going to restrict the screenshot to this region, make sure I get the labels on the axes. This is now on my clipboard. So if I'm doing an all electronic workflow, I could go to my Word doc and I could paste that in as the results of my investigation and the relationship my group discovered between net force and acceleration. So 3 options for preserving things about SPARKvue. Again, most of the time in the essential physics investigations, your students' responses will be sufficient on the handout that's provided to them, but these are some options for saving and sharing information from SPARKvue, aside from things like sketches. All right, so a question to you. We've now seen 2 investigations. Let's imagine that we just did the Newton's second law investigation and we had some students that were absent. All right, there was a band trip or something like that. How would you support a student who missed the Newton's second law lab day? What is your policy on lab makeup? What sort of accommodations do you make, if you make any? Let us know in the chat if you have an approach to this, and then I'll show you one option that the portal and Essential Physics program provide. Give you a moment there. The question is, how would you support a student who has just missed the Newton's second law lab day? All right, Marie, thanks for the suggestion. They have to copy the lab from their colleagues. Yeah, definitely. You might have a lab group and they could go to the lab group and get that data. In the case of this particular investigation, you could decide whether you want them to get the final data or whether you want them to get the file and do that analysis themselves. Since this is a fairly involved lab, there are different stages where they could get that data. Thanks for the suggestion, Marie. Ken mentions, seems like there's a plethora of materials to supply a student to catch on and apply the student work material. Yeah, so I know Ken was in our previous session and perhaps has some additional knowledge here. Keep those suggestions coming, but what I want to mention to you is, wouldn't it be nice? Wouldn't it be nice if there was a pre-created video that you could show to students of this data collection? In a perfect world, you would create this video or one of your students would create this video, but we know that time is limited. So we've actually done something like that in the form of what's called the PASCO Academy. Let me show you, let me describe what these resources are, and then I'll show you how to get to Academy. So in Academy, for Newton's second law, it includes a student-directed video, that is some physics teachers talking to the audience as talking to a student, that introduces the topic of Newton's second law with a little demo, and then actually goes through the entire lab showing the collection of data just as I would have here, except they go through all 5 runs. All right, so full data collection for this lab in SPARKvue with good camera angles showing I'm adding a mass. Here's the data I get in SPARKvue. All right, so that exists. I'll show you where it is in the Academy shortly. So that exists, plus that data that was in the SPARKvue file collected in the video, we actually give you that file. So you could give students the actual raw data that was recorded in the video, not data like it, but the data file from the video. So that's about as good as if they were there and just observing, right? Or it's like Marie's suggestion to get the data from another student, but here they see the actual data collection, making that association with where the data came from. Next up, there's a student lab handout for use with the video. Now, why do I say for use with the video? Well, sometimes the video doesn't allow, the video doesn't allow students to be there and collect data. So the physics teachers in the video have sometimes adapted the student lab handout to maximize the data analysis that students do, sometimes providing them data from the video in the handout to get them a jump start. So the student lab handout is much like the one that you would find in the teacher resources for the particular lab, but it has sometimes been changed to be especially useful for use with the video. There is a video which you could give to students after they do the analysis that has our physics teachers walking through the analysis with them. I wouldn't give it to them up front because we want the students to do the analysis, but that video is a follow-up video called Student Follow-Up. Then there's a teacher answer key specific to the video data, analogous to the teacher answer key for the generic data that's in the lab itself, but for the specific video data. And there's also a teacher preparation video that tells you what's going to happen in the student videos. All right. So those are the resources in what we call the PASCO Academy. And Guy asks the perfect question in the chat here. Do you need portal access for the Academy materials? The answer is no. There are 2 ways to get PASCO Academy. So how do you get access to PASCO Academy? The first way is if you have teacher access to Essential Physics, you log in as you would to get the ebook at education.pasco.com, and there is a button to get to Academy. So I'll bring that up to make it concrete. So if I am, sorry, wrong browser. If I am logged in as a teacher to education@pasco.com, there is a button that will get me directly to Academy, where you can see we have 25 different topics, and topic number 3 happens to be the Newton's second law one we're looking at, and these are all those resources that I just outlined. Yep, thanks for the segue, Guy. Now, hopefully some of you are asking, well, if I have Portal, can I get Academy access? And the answer is yes, it's included with Portal access. And in fact, all our academies are included with Portal access. The one we're interested in today is physics, but it also includes a chemistry academy and a biology academy. Similarly with teacher videos directed at students and included data files. So how do you get there in the portal? I'll bring up my portal browser here to illustrate it. Inside PASCO portal, we go to the main menu, and it's under curriculum under PASCO Academy. And again, this is included with your PASCO Academy subscription. We get the physics, chemistry, and biology portal academies rather. We click on it, and here's the Newton's second law with all those same resources we just talked about: student videos, teacher video, student files, teacher files, with all the same distribution methods that are available via Academy. Via portal. All right. So with this, now that you know the resources in the Academy, let's talk about some of the opportunities to make it useful. I probably mentioned it was created at the height of the pandemic when schools were closed. We wanted students to have some way to still do data analysis in physics. So how do you foresee using the resources? Our time is a bit short, so let me speed through some possibilities here. We've already talked about what if a student is absent. They could use the resources from the Academy that you provide to them at the timing you provided to them. You're in control of that via portal or the Academy resources outside of portal. And you can help students make up a lab, the best alternative to being there. You could support remote learning, which was the original design during the height of the pandemic school closures. You could use it as a resource for substitute teacher day. If you are planning to do Newton's second law next Monday and it turns out you can't make it, you could direct your substitute to the portal Academy, the Academy inside or outside portal, and you could use those resources as a substitute, and it's basically hit play if they don't know the topic inside and out. You could use it as teacher preview if you want to just get a sense for a way to introduce a topic. Our physics teachers with years of experience share the way they introduce the topic with you, and you could just replicate that or just use the student video excerpt from that. It's an alternative to hands-on labs if the time doesn't permit or if the equipment doesn't permit. We are PASCO, we're big advocates of doing hands-on investigations. It's core to our mission. Sometimes it's not possible though. And in those cases, PASCO Academy could step in. And finally, you could give it to students as a review. Here's a lab we didn't do, or here's a lab we did, different approach. See if you can test your understanding or cement your understanding via these resources. So if you have additional thoughts on how the Academy could be used, please do share them in chat. With that, though, we are going to continue to one final investigation. We have about 15 minutes left, which I think is sufficient time to take a look at one final investigation that uses something other than the smart card, something that's included in the standard kit for essential physics, the E&M module. This is resistors and Ohm's law. I'll bring up the equipment here. And this and other electricity and magnetism investigations use what we call modular circuits. And again, this is included in both levels of the essential physics kits. What is modular circuits? Well, the classroom dilemma that we're trying to address with modular circuits is the following. Students see diagrams, circuit diagrams like you see on the left, and then they proceed to use breadboards traditionally or a bunch of wires and have a tangled mess. What if we could have the circuit diagram that they see be associated with the physical configuration? It helps them make the connection between these two things, and big hint, it really helps you troubleshoot things because you're no longer looking at a pile of spaghetti to try to help them troubleshoot their circuits. You're now looking at the circuit diagram in physical form. So as you can see from the live video here, I have set up the circuit for this for this resistors and Ohm's law investigation. I'm not going to dive into the resources available here because we've seen how to access it both from the teacher ebook sidebar and from the portal. But again, all the same resources exist, from handouts like this for the student instructions, to slides, to teacher video, etc. And it's in the Academy as well. All right, so how do we do this investigation? Well, in this investigation, what I've done is I have set up the circuit as described in the handout. I will bring up a PDF of the handout just to guide us through the investigation and allow us a shortcut once we know how it works. Right. So here is this investigation, and it's basically going to have students investigate the relationship between two things: the relationship between the current through a circuit and but the current through the circuit as we put various resistors in this circuit. So there's a table here where we can record our data. Here is the image of the circuit and the circuit diagram. As you can see in the video, we basically have a single AA battery in this module, and we have it hooked up via some corner modules to a switch that allows us to open and close the circuit. And we have the ability to put in a module up here in this empty space that is a resistor. We have a choice of resistors here. I'm going to do 4 of them today, from 10 ohms up to 330 ohms. But let's talk a little bit about modular circuits. Each of these modules is a physical module that can snap in to make a physical connection. In order to make an electrical connection, though, we need to join it via little jumpers. These jumpers are clips included in the kit. So I'm going to insert and connect these 10 ohm resistor for our first measurement by clipping it in with these clips. The circuit is still open because I have the switch open. What we're going to do next is recognize that, well, this is an investigation. It uses SPARKvue, so it's going to begin with a file that we open, in this case, 17C. I'm going to return back to the installed SPARKvue app, but again, we could do this with the PWA. So investigation 17C is resistance and Ohm's law. It opens to a simple digits display. And in the first part of this investigation, students are asked to connect the current sensor. Now, you might not see a sensor here, but in the case of modular circuits, we wanted to emphasize in circuitry that you make current measurements in series. So the actual sensor is a module. It is this module right here already connected, and there is built into this a current sensor. We call it the wireless current sensor module. So I'm going to turn it on just like I would a standard sensor and go into SPARKvue. Since I'm using the native SPARKvue app, I can simply click on Bluetooth and see my current sensor here, identify it by its 6-digit ID printed on the sensor, hit done, and I'm now connected. I have the start button. And in this investigation, students are going to simply press start to see the current reading, and then close the circuit and record the current that they're getting there. So with a 10 ohm resistor, I'm getting 0.1444 amps. So let me record that directly in the table. And that was with a 10 ohm resistor. So I'm simply going to swap out the 10 ohm resistor for the next module, 33 ohms. SPARKvue is still recording in this digits display. I'll close the circuit and I get 0.045 amps, which I, as a student, can type in for my 33 ohm resistor. And I'm just going to continue here. I only have 2 more, so it'll be quick. The modular circuits essential physics kit also includes a 100 ohm resistor, which will be our next measurement. And for that, we see 0.015 amps. And that's the last module, but if we want to extend this to greater resistances, there's also a spring clip module included in this kit, along with a couple of more traditional resistors. I have inserted into that spring clip the 330 ohm resistor. And when I close the switch for this final one, we see 0.004 amps for 330 ohms. All right. So students following this or the slides that you can project, that version of it, will be asked to go over here and type in these currents. This is going to look a lot like the lab we just did in Newton's second law. Can we discover a relationship between these 2 measured variables? So I'll quickly type in these values. And of course, as soon as I get pairs here. Thank you. All right, there we go. And I'll scale the fit. Our graph here, this graph, expand it, is a graph of current, measured current versus the resistor's resistance. Once again, let me just turn off the connecting lines via the graph settings so we can see those 4 dots. And now clearly this is not going to be a linear relationship. You just test it to show it. But there are a bunch of curve fits built into SPARKvue's graph for discovering other types of relationships. I could ask, is this inverse square? Maybe. I can change that to all these other fits and see which might be most appropriate. And hey, from the mean squared error there and the visual fit, excuse me, it looks like that is quite a good fit. So it seems that we have discovered an inverse relationship between current on the y-axis and resistance on the x-axis. So kind of a confirmation of Ohm's law. Now, this actual lab goes on to have students linearize this relationship by hand calculating the inverse resistance and typing that in to get a linear fit. It has a part 2, and in part 2, they're going to say, well, now that I know Ohm's law, could I figure out what the resistance is by simply measuring the current and voltage for an unknown resistance? And in this case, it is the light bulb module included with this. So they would do this and add to this experiment one final sensor, and that is the voltage sensor, which they can use to measure the voltage across this and estimate from Ohm's law, an application of Ohm's law, what the resistance must be. All right. So that in a nutshell is another investigation. You can see it follows those same parameters. It's using SPARKvue and sensors. We begin by opening the experiment file and proceed to collect data guided by the student handouts and or the slides provided to you in the teacher sidebar if you're not using Portal, or in the Portal if you are. All right. And when things go awry, remember the Academy is there for you as well as the support. All right, so we are nearing the end here. A couple of things to review and extend our learning today. There is a great video guide on essential physics. We've talked in part 1 about video guides for students on how to navigate the ebook, for teachers on accessing the resources in the ebook sidebars. There's one more video that is great for introducing you and our students to all the core features of SPARKvue that are used across all of the essential physics labs. This is a video about SPARKvue, but it's tailored to those features that are used in essential physics investigations. You can find this in the student or teacher ebooks help section by clicking the help button on the ebook homepage. You can also find it in the video guides on PASCO Portal. This next thing is the first thing I'm showing you that is Portal exclusive, and that is in the Portal, we include a professional learning section. And in this professional learning section are videos and other things most relevant to our discussion today. There's a full self-guided course on essential physics with equipment. And if you take this course, you'll do a deep dive into the resources for students, teachers, and the use of sensors. You can find this in the Portal by going to the menu, professional learning section, courses with certificates, where you'll find the course called Essential Physics 3rd Edition with Equipment. Take it at your own pace. If you want to learn a lot more about SPARKvue, we also have in there a course on SPARKvue Essentials that will dive much deeper into SPARKvue features. But again, remember that video, that few-minute video I highlighted on the previous slide, is essentially a quick intro to all the features of SPARKvue that you use in essential physics investigations. What if you need more support? Well, whether or not you're a Portal user, you can go to pasco.com/support, connect with customer service tech support or your local PASCO rep. If you happen to be a Portal user, you can also go to the technical support section in Portal by going to the menu, support, technical support, contact them directly. And there is a very useful PASCO Portal help section here. This is a help guide for Portal itself. And for those of you who are using, for example, LMSs, there's some great information in the PASCO Portal help about connecting it for your administrators to your LMS, or using it as an instructor to get your content into your LMS, whether it's Google Classroom, Canvas, Schoology, etc. So that help system has some more details on that are beyond the scope of what we can show here today. All right. Finally, if you have any questions, don't hesitate to contact your local PASCO rep at pasco.com/support. And thanks, Kane, for pasting all those links in the chat. So with that, we're going to end the recording.